Okay, so now we're on the unit where we're talking about parametrics, vectors, and polars with calculus. Okay, so this is the first part of it that is going to be talking about the parametrics themselves. So it's been a while since we've done parametric equations, but remember they're basically giving x values or parameters and y parameters in terms of t, because of course our parameter for parametrics is time in itself. Okay, so we're going to make the table, and then we're going to sketch the curve, and then we're going to show the direction of the graph. And if you see already, I have a t column, an x, and a y column. And what I did was I chose time of 0 as a default because i.e. there is no quote-unquote negative time. However, if we did say that we started 2 seconds ago, t could be -2, okay? It's saying that you started 2 seconds ago, where that -2 actually in all actuality is 0 in itself. That's when the time started. So in this case, we're going to start with 0, and then we're going to see what the table produces, and then we'll go from there as far as that negative time interpretation and whatnot. Okay? So we have 0, which if we, of course, put 0 into the the parameter for time, we would get an x position to be undefined because, of course, we can't take the negative of the square root, or sorry, the square root of a negative number. And then y, if we put 0 over here for t, we'd get 2. But the fact is that it's going to be undefined. So at time is equal to 0 per se, we're not going to have an actual location of a point. But when we do have the time of 1 inputted into t, we would get the square root of 0, which of course yields 0 for the x, and then the 1 would yield 3. So my points end up becoming this 0, 3 is that time 1 point. That 1, 4 is that time 2, and I'm over here on the graph. And then square root of 2 is approximately 1.4, so 1.4 at 5, and then 1.7 at 6, and last but not least 2 at 7. So it did ask us to indicate the direction. That's why we have these arrows, the blue arrows that you see. And it's saying that that's the direction that the parameter or parametric equation is creating. And then we have that arrow there at the end saying that it'll just keep going on forever and ever, because it didn't give us an interval, a specific one to just analyze. Okay, so it's been a while since we've eliminated the parameter as far as solving for t, which you of course see that I took that x parametric equation, I solved for t by squaring both sides, adding 1. So then I plugged in that value for t, which is x squared plus 1, where t was, into the y function. Of course, this is the xy Cartesian plane. We're going to use this coordinate system just like normal. Y is equal to whatever function, or f of x equals whatever. We'd get x squared plus 1, then plus the 2 to get x squared plus 3, which of course looks like it's a parabola shifted 3 units up. Just keep in mind that we are starting with time is equal to 1, therefore just like you would normally label a parametric equation, or the function that is, you would put time is equal to 1, 2, 3, 4, and 5. And when I say function, I mean graph, because these parameters sometimes, these parametric graphs, do in fact fail the vertical line test. So they're not necessarily always having to become functions. A little bit of review there. They're just graphs in themselves. Okay. The next one, we have the parametric for the x. So you see that parametric equation for x is t squared minus 3, then 2t for y. But the difference here is that it's showing specifically only between time -2 and 3. Okay. Now, just like we talked about last slide, you don't necessarily have quote-unquote negative time, but in this case, the way it's giving it, we're going to put -2 saying basically 2 seconds ago, okay? So if you were to say 2 seconds ago, yes, in reality, you would start the time here, but if something is existing even before, you could start the timer at time is equal to 0 and say 2 seconds ago it came from this location, okay? So that's that interpretation of negative time that we see here graphically. So we put -2, -1. We're using all the time values that it's asking us to analyze, and then we're just plugging them in just to get our xy points. And you see from the graph, plotting those xy points, we have 1, -4, -2, -2, so on and so forth, which yields this graph in the direction that it's going. Okay, and again, as you already see the blue arrows showing you that it is starting at this initial point, but then it has a direction going of that direction. Arrows going that direction. Because it closes and ends at 3, it will stop and not continue to go past it. Okay, so a little different there as far as just showing you that piece. The same like we did last slide. If we're solving for t, to get t by itself, you'd add 3 square root both sides. You remember that when you square root and initiate a square root, you should have a plus or minus to it. And again, just like I just mentioned, these aren't necessarily functions, but they're graphs, in this case, that failed a vertical line test, like you see here. So the way you see this y is equal to plus or minus 2, because you're plugging that t that you solved for, right here, you're plugging it into the y function, you would get plus or minus 2 times, there's multiplication right there, the x plus 3, which is a parent function of square root of x, but the difference here is it's a parent function of plus or minus square root of x. So there's that bottom piece added to it. Of course, it's plus 3, so we shift it 3 to the left, which you see this shift right here. And then the magnitude is multiplied by, so it's a vertical stretch by 2, which clearly the graph is showing all of these features. But remember, just like it gave us a bounded interval, we would only graph that specific interval showing from -2 all the way to a time of 3. Okay? And it's units. You could put seconds, minutes, but if it's nothing there, obviously it's just going to be units, time as far as units go. Alright, so here we don't have, again, we don't have an interval, but we can start with a fundamental time is equal to 0 and see what the graph looks like. So starting with time is equal to 0, you're just plugging that into these functions. And a little bit of unit circle review. The cosine of 0 is 1. Where we multiply 1 with 2, we'd get 3 plus 2 is 5. Okay? And then we would plug in 0 for the y parametric equation to get sine of 0 is 0 times 3 is still 0. And -1 plus that 0 is still -1. So my point at time is equal to 0 is 5, -1. That's my initial value. And then plugging it in, we all know the unit circle, so I don't want to drag this out. Putting pi over 4 into where t is at, you would just use the unit circle, and square root of 2 is approximately 1.4. So when we're adding that with 3, we get 4.4. And then the other one, it would be that the pi over 4, the sine of pi over 4, is going to be that root 2 over 2, which you're multiplying with this 3. And that's where we get this. And we know already, root 2 is about 1.4-ish. So divided by 2 is going to be 1.4 is going to be about, what am I thinking right now? Okay, so like I was saying, that root 2 is 1.4. And if I divide it by 2, I'm going to get like a 0.7-ish, if you will. And 0.7 times that 3, just caught my mistake, would be about 2.1, not 1.8. So the -1 plus the 2.1 would yield a 1.1, not a 0.8. So this would be about 1.1. So at 4.4, it's going to be about 1.1. So let me go ahead and fix the graph just a little bit here. This second point ends up moving up just a little bit. So that would be 4.4 and 1.1. Alright. So that's the graph, and it's still going that direction. So you have this showing there. And then you have the other points in themselves. Pi over 2, which is 3 and 2 that it yields. And then so on and so forth from there. Let me see. Yeah, everything else should be correct. If not, I'm sure I'm going to get the emails that some things aren't. But you notice on the graph, you have the initial value, and then it shows the arrows showing the direction that the parametric graph is going. And it's going this direction. and make sure that you do label the time as far as the points are concerned. Okay, so just a little review as far as graphing parametric graphs. Now let's move on to parametric equations in calculus. So if a smooth curve, we know this from just basic differentiability, has to be a smooth curve, otherwise it's an undefined slope from cusps and other things like that, vertical tangents, removable discontinuities, all that, is given by the equations, the X parametric equation and the Y parametric. And notice that it's going to still be with my parameter of t, of course. So the slope of c at a point, so it's basically saying that dy dx at a given point is going to be, the slope is equal to dy over dt divided by dx over dt. And you know that you can't have a denominator of 0, so it's just a little caveat warning there saying, remember that your denominator cannot equal 0. So how did they get this dy dt over dx dt? Well, if I were to write this out, I get dy dt right here divided by dx dt. It's the same as multiplying by the reciprocal, and you can see that these cancellations occur, which reduced form would give you those differentials combining together to form the dy dx in itself. Okay, so now let's look at the second derivative. Second derivative is a little bit tricky. It's basically taking, in respect to x, the derivative of what you got from over here, meaning the first derivative. Okay, so right here, where I have dy dx highlighted in orange, remember from our first derivative rule that we highlighted up top, we know that dy dx is equal to dy over dt, which is what I highlighted right here, over dx dt. Okay? And the only bit that's left over is this green stuff that I've highlighted that shows you it's just the derivative in respect to x. Okay? So basically what it's saying is you're going to take the derivative of the resulting thing in respect to x. And you'll see what that looks like here on the next couple of slides. Alright, given the parametric with no calculator, given the parametric equations, x is equal to that, y is equal to this, find the first and second derivative. Okay, so by the equation, dy dx is equal to the derivative of y in respect to time over the derivative of x in respect to time. Now they've already given these as functions written like x is written in terms of t and y is written in terms of t. So all we have to do is, because it's written in terms of t, is derive in terms of t. So deriving y gives me, okay, so we're deriving y, we get 20t to the fourth minus 18t squared. Now the derivative of the x parametric is just going to yield 2x. Again, because dy over dt over dx over dt yields dy over dx. And now it's just a matter of GCFing out this 2t, common factor, and then reducing to a simplest form of 10t cubed minus 9t is your dy dx function. Basically f prime of x. Okay, so now let's look at this second derivative. We're taking the derivative of what we just got as an answer, but we're taking it in respect to x. Okay, so what that means is, if I were to look at this, and now I'm highlighting dy dx is equivalent to, okay, it's equivalent to dy over dt on top, and then over dx over dt. And all we're going to do is take the derivative of that. Okay, so when we take the derivative of that, it's like saying we're going to take the derivative of our answer, and we're going to take it, and my answer being this guy right here. So my answer is I'm going to take the derivative in respect to time. Okay, so this is equivalent. I'm going to take the derivative in respect to time of what I got as an answer of dy dx. So there's a little bit of manipulation that I just did there to show you how these are equivalent, but how ultimately the way it's going to simplify is you're just going to take the derivative of the dy dx function and then divide it by dx dt, because it's still equivalent, showing you the second derivative. And if you need to rewind this video to see what I did, by all means do so. So this 10t cubed minus 9t, when I derive it, there's that top portion part. Basically the derivative in respect to time of what we got for the first derivative. But we need to make sure that we remember that this is going to be over dx dt. That means my original parametric I'm going to derive, and I get that 2t piece. And then nothing's going to GCF out and cancel, so that your second derivative is going to be 30t squared minus 9 over 2t. Okay, and you see that it is written it was taken in respect to x, but written in terms of t. That's what's different about these parameters. They're not written in the terms that they're taken in respect to, per se. Alright, second example. We were given the parametric equations, y is equal to 5 sine of t, and y is equal to 3 cosine of t, and we're trying to write an equation of a line. So there's a function there. Now we're going to go back to way long ago when we were finding f of x, or the point slope formula of y minus y1 equals m times x minus x1. And it is the tangent line, so there's not going to be any negative reciprocals like there would for normal lines or anything like that. It's just going to be a regular basic tangent line, and our at value is that. So it's basically saying we need a point and we need a slope. Okay? The point, like right here, the progression that I'm showing you, the point is xy. And that will come whenever we're looking at the time of 2 pi over 3. So if I put the time of 2 pi over 3 in for here, and for here for this t, I would get x's component as the following, and I'd get y component as the following. Now just doing what I know of unit circle and simplifying, I get my x value is 5 root 3 over 2, and my y value is negative 3 halves. So my point just became 5 root 3 over 2, and negative 3 halves is my xy value. Now, from what we just learned on the last couple slides, we're going to take the derivative, the dy dx, okay, and we're going to evaluate it at 2 pi over 3, because we're basically trying to find f prime of 2 pi over 3. Okay, like what is that slope? Well, per the equation that we just learned, we know that dy dx is dy dt over dx dt. So we go back to our parametric equations, and the derivative of 3 cosine of t yields negative 3 sine of t, over the derivative of 5 sine of t is 5 cosine of t, and then we're just going to evaluate it at the specific x value. So we just plug them in like you see here, and it reduces as far as a 3 root 3 over 5, positive root 3, or positive 3 root 3 over 5. So just plugging it in, y minus y2 is equal to m times x minus x1. Your answer would be there at the bottom right hand of the screen. Okay? Let's do another one. This one says find all points of horizontal and vertical tangency. Okay, so where it's tangent horizontally, we know the derivative is 0. Where it's vertical tangent, we know that the derivative is undefined. Otherwise now dy dx is 0, dy dx is undefined. Nothing new. Given the parametric equations that you see here, 3t squared minus 6t and t squared minus 8t plus 9. Per the function, or per the definition of the derivative that we just found with parametrics, it would be the derivative of the y, which is the derivative of y. Ooh, I just noticed something. Okay, so the derivative of y in respect to time over the derivative of x in respect to time. So I did it backwards. I did dx dt over dy dt. Glad that I caught that before I got the emails. So it would be 2t minus 8 over 6t minus 6. Okay? not this guy right here. So we're looking at dy dx. Okay, so when would it equal 0? So I have these backwards, and since I already have them pre-filled, I'm just going to swap these real quick. It will equal 0. The slope will equal 0 when the numerator is equal to 0. Okay? Which would be at time is equal to 4. The slope will be undefined when the denominator is 0. So I'll put undefined when 6t minus 6 is equal to 0, which would occur at time is equal to 1. You see the table that I just filled out here, so I could get my x and y. Let me check this as I go through. I would get 3 minus 6 is a negative 3, and I would get negative, yep, that one does work out. Negative 7 plus 9 is 2. So negative 3, 2 is the first point, and 24, negative 7 would be the other point. All right. Earlier in the year, we learned to find the arc length of a curve, okay, and over an interval like a to b. The arc length of a curve is 1 plus f prime of x. In this case, you could write h prime because we're dealing with assignment of y is equal to h of x. So it's 1 plus the derivative of that function squared. Okay, so you take the derivative first. I know it's been a while since we've done this. Take that derivative first and then square it, and then square root that sum. That is what it would be as what we've learned before, and it would also be equivalent to dy dx, because that's what h prime of x is. All right, so what we're going to do now is we're going to see parametric equations, okay? Meaning you have the f of t and the g of t. So if I want to take the arc length of a parametric equation, this dy dx that I had here, okay, that I'm going to start writing right here, is equivalent to this dy dt over dx dt, because of how we know the algebraic manipulation happens. This squared is going to apply to both the numerator and the denominator. And then you notice next we get a common denominator so that we can combine the numerators together. So it's like multiplying this 1 right here by a form of dx dt squared over dx dt squared. Okay, so you see that we only have this one common denominator written. And then we have this, the square root is basically broken up on the numerator and the denominator piece, because we know that it's equivalent to that. And the dx dt squared will cancel and just become dx over dt. Okay? And then the top remains the same. It's just the square root of the summations of the dx dt. It almost looks like the square root of a squared plus b squared, like the distance formula, if you will. But it's looking at parametrics in that respect. Okay, so that you see that distance formula again, or the Pythagorean theorem, if you wanted to look at it that way. It's like the hypotenuse filled to it. So anyway, so there we go. So the equation that you're going to know is dx dt is basically the derivative in respect to time. No longer x, but in respect to time. And then g is then derived in respect to time. And then we square each one, take the square root of that summation, and we would integrate it. This would be the arc length, which is what you see here. This would be the arc length for a parametric graph. Okay, so length of the arc of a parametric graph. So it's the square root of dx dt squared plus dy dt squared, and you're integrating in respect to this t. Okay, so something to take note of. The formula works when the curve does not intersect itself. So you're going to have to maybe look at the graph in itself, put it in the calculator, and see, does it overlap itself at any point in time? And the curve must be smooth, otherwise you cannot find this arc length. Okay, so those are the stipulations there. So here's a non-calculator example. I have a parametric of x is equal to e to the 5t plus 2, and then y is equal to 3 sine of t squared. We do have our interval given from 0 to 4, so that's easy to set up. And then from the equation, this is the square root of taking the derivative in respect to time and squaring it. And I know it's been a while since we've done this. It's going to be a lot of, I'm going to say that a lot as far as it's been a while since we've done this, or it's been a while since we've done that. But let's go ahead and let me erase this so you can see what it is. We're taking the derivative of an exponential function per se, which is the carbon copy. Let me highlight it as I go. The carbon copy times the natural log of the base times the derivative of the power. And then we're going to square it. So that 5 squared becomes 25. This exponential function is squared. And we know that 2 can be distributed to the power so that it becomes 10t plus 4 is the power of e, and it's 25e. This is its most simplified. And then the other part is this squared is going to apply not only to this 6t to become, whoops, forgot something. Glad that I caught it. It becomes 36t squared. So that's a 36t squared right there. And then that squared also applies to the cosine to become cosine squared. And your final reduced answer would be that. And it said do not evaluate, so we'll just leave it just like that. Alright, that's it, guys.